Then third type, ferromagnetic material or solid. Then fourth one, anti-ferromagnetic solid. Then fifth one, ferromagnetic solid. Ferromagnetic solid. Okay. Last class we discussed these two. Okay, and I have told you in diamagnetic and paramagnetic. In diamagnetic solid, if you keep a diamagnetic solid in a magnetic field, diamagnetic solids are weakly repelled. It is repelled by the magnet. Diamagnetic solids are weakly repelled by the magnet, whereas paramagnetic solids are weakly attracted by the magnetic field. Okay, so this is the characteristic of diamagnetic and paramagnetic solids. And I have told you, in paramagnetic solid, they usually, the atoms or species present in the solid, they usually contain one or more unpaired electrons. Okay, it consists of one or more, okay, the atoms or ions or molecules present in the solid, they contain one or more unpaired electrons. Okay, today what we are going to do, we are going to learn the ferromagnetic solid. What is meant by ferromagnetic solid, and how a ferromagnetic solid respond to the external magnetic field. Okay, so that's what we are going to do. Ferromagnetic solids. We write the next page. Ferromagnetic solids. Yeah, some solids are strongly attracted by the magnet. Solids like nickel, right, iron, cobalt, these solids are strongly attracted by the magnet. We call these solids as ferromagnetic solids. So ferromagnetic solids are general, they are strongly attracted by the magnet. I have told you, we classify the material based on the response. Okay, if you keep the solid in a magnetic field, how the solid will respond. Okay, so ferromagnetic solids are basically solids which are strongly attracted by the magnet. They are strongly attracted by the external magnetic field. External magnetic field. So if we keep the material in a magnetic field, this material is strongly attracted. Okay, what are the examples? Yes, we have few examples like iron. Okay, the element iron, then the element cobalt, then copper, right, iron, cobalt, iron, cobalt, nickel, iron, cobalt, nickel, then the element gadolinium, okay, and the compound chromium dioxide, CrO2. These are all few examples for ferromagnetic materials. They are strongly attracted by the magnet. Okay, iron, cobalt, nickel, iron, cobalt, nickel. This is gadolinium, which belongs to lanthanide family. Gadolinium, and this is chromium dioxide. Chromium dioxide. Okay, these are all few solids which show ferromagnetic character. Okay, why? What is the reason for these materials showing ferromagnetic character? What's the reason behind? The reason is, in these solids, right, if you take, say, for example, a piece of iron metal, these solids, okay, they have unpaired electrons, no doubt in that, right? Atoms or species, okay, you can say generally as species. Atoms or species contain more than one unpaired electron. They usually contain more than one unpaired electrons. These materials usually contain more than one unpaired electron. Okay, and another important feature is that, see, suppose you keep the solid, say for example, I'll take some external magnetic field. Okay, this is north pole of magnet and this south pole. Now I'll keep a piece of iron solid here. I'll keep a piece of iron. If we keep the solid in a magnetic field, the solid get magnetized. It is attracted. Good, strongly attracted, that we know, right? After keeping the solid for a few minutes in the magnetic field, then remove the solid, right? If you bring any other magnetic material, say for example, you take a piece of another iron rod, another iron needle or something. If you bring it close to this needle also get attracted by this iron. Students, listen carefully. I am just keeping a solid iron, okay, in a magnetic field. If you keep it for a few minutes, the material get magnetized. Immediately it get magnetized and it is attracted. Then see, the moment you keep the iron piece in a magnetic field, the iron piece get magnetized immediately. Then remove that piece, okay, and to this piece you bring a needle of iron close to that. That needle get attracted. What is meant by that? When you keep the iron piece in a magnetic field, the iron piece get magnetized. That magnetic character remains for some time in the material. Okay, then after a few minutes, slowly the magnetic character will disappear. That is the very good nature of ferromagnetic materials. See, in the case of paramagnetic, I have told you paramagnetic solids are weakly attracted. But if you remove the paramagnetic solid from the magnetic field, the solid will lose the magnetic character immediately. Whereas in the case of ferromagnetic solid, if you keep the ferromagnetic solid in a magnetic field, if you remove from the magnetic field, even after removal from the magnetic field, the magnetic character will remain for some time. If you bring any iron needle close to that needle get attracted by this piece of iron. Okay, so the magnetic character remains for some time. Then slowly the magnetic character will disappear. Okay, so this is the one important feature or the property of ferromagnetic solids. Okay, this is very important. Now, why these solids shows this type of property? Why they are strongly attracted by the magnet, and why the magnetic field remains for some time even after you remove from the magnetic field? Okay, what is the reason? The reason can be explained based on the domains that exist in the solid. Let me explain with the domain theory. Students, listen carefully. Solids, okay, some solids, they have or they possess what are called domains. Domains. What is meant by domain? See, suppose if this is a solid, okay, this solid has lot of domains. Let me just show you few. Okay, these are all domains. Listen, before keeping the material in a magnetic field, okay, each ion atom, students listen carefully, each ion atom has unpaired electron. How many unpaired electrons are there? Listen, for iron, you know very well the electronic configuration is 20, atomic number is 26. So the outer electronic configuration is 3d6 4s2. For iron, the outer electronic configuration is 3d6 4s2. You all know that S subshell maximum capacity is 2. So in the S subshell we have 2 electrons. So these 2 electrons should be paired. In D subshell you can place maximum of 10 electrons, but now we have only 6. So what I'm going to do, you take D subshell. D subshell consists of 5 d orbitals. Okay, I'm going to fill this d orbital with the 6 electrons. 1, 2, 3, 4, 5, 6. See, we have 4 unpaired electrons. Each ion atom has 4 unpaired electrons, and these 4 unpaired electrons will give a net magnetic moment. Okay, will give a net magnetic moment, and you know very well magnetic moment is a vector. Magnetic moment is a vector. So each ion atom present in the solid has a magnetic moment, net magnetic moment. That magnetic moment has direction. Okay, let me show that here. Students, observe this carefully. Now I have taken a piece of iron metal, where lot of iron atoms are there. Each iron atom has a net magnetic moment, and that net magnetic moment I am going to show as vector. Okay, so here these arrow mark indicate an iron atom, right, with the net magnetic moment. The net magnetic moment are aligned randomly, okay, randomly like this. Yes, that's a random arrangement. This is one domain, this is another domain. Okay, like this there are so many domains present in solid, right? In all these domains ion atoms are there, but I'm showing the net magnetic moment of the ion atom with the arrow mark like this, because magnetic moment is a vector. It is randomly oriented in all domains, right? The magnetic moments are completely random. That's a random orientation. Okay, I'm just drawing this randomly like this. That's a random orientation. So before keeping in magnetic field, before keeping in external magnetic field, okay, before keeping in magnetic field, the magnetic moments, okay, magnetic moments are orienting, okay, in a random manner. That's a random orientation. Random orientation. Okay, that's a random orientation of magnetic moment exists. Now what I'm going to do, if I keep this solid in a magnetic field, what will happen? See, before keeping in magnetic field, the orientation of magnetic moments are random. Okay, the solid does not possess any magnetic character. Now I'm going to keep this solid in a magnetic field. Okay, the moment you keep the solid in a magnetic field, what will happen? Let me show you in the next page. Assume that I am taking the same solid and I am showing some domains. Okay, now we are keeping the solid in a magnetic field. say this is north pole and this is south pole, right? And you know very well there are magnetic lines of forces passing, right, from north pole to south pole. I'm just showing like this, okay? Magnetic lines of forces passing like this. Now the moment you keep the solid in a magnetic field, students, I'm taking the same solid iron metal, okay? I'm keeping the iron metal in a magnetic field. The moment you keep in a magnetic field, what will happen? The magnetic moments of individual iron atom, they start to orient in the same direction of the external magnetic field. All domains, in all the domains, okay, the net magnetic moment start to orient in the same direction, okay, as the direction of the external magnetic field. Once all magnetic moment starts to orient in the same direction of the external magnetic field, then your material get magnetized. Your material get magnetized. That is why it is strongly attracted. Okay, it is strongly attracted, right? Suppose if you remove the material from the magnetic field, suppose what happens is that, right, I'm just roughly drawing, assume that the same material, okay? If you remove the material from the external magnetic field, okay, this alignment will persist for some time. Even after the removal, okay, the alignment, some magnetic moment starts to orient, starts to become random, but most magnetic moment will still remain in the same direction. Will still remain in the same direction. And some randomization starts, but most of the magnetic moments orient, okay, remains orienting in the same direction. That means even after the removal of the material from the magnetic field, the magnetic character persists for some time. That is why if you bring any needle, iron needle, near to this, okay, that needle get attracted. Why? Because even after the removal of the material from external magnetic field, okay, the orientation of the magnetic moment, orientation of the magnetic moments of individual atoms, it remains as such for some time. Okay, that is the reason why the material still remains magnetized. Is this clear, student? Any doubt in this? Now what will happen as the time progress, due to the thermal energy, okay, suppose at room temperature, if you do this, okay, due to thermal energy available at room temperature, right, these magnetic moment, okay, by absorbing the thermal energy, they start to disorient. Due to thermal energy, thermal disorientation, or because of thermal energy, right, these oriented magnetic moments starts to disorient, or it become random again. So randomization starts as the time progress. Right, randomization starts. Okay, what is meant by that? These aligned orientations starts to orient in different directions. So after some time, what will happen? It will become again random. Once it become random, then the material will lose the magnetic character. Is this clear, student? But for the randomization, it will take some time. During that period, your material will act like a magnet for some time. Okay, this is the important character of ferromagnetic solids. Okay, students, any doubt in this?
No, sir.
Yeah. Okay, so this is what is called a ferromagnetic substance, right? Good. Ferromagnetic substances, right, can be used as or we can make it into permanent magnet, okay, by applying the magnetic field, right? Okay, so this is very important, keep this in mind. This is what is called the ferromagnetic substance, right? Let me repeat. Listen, see, ferromagnetic solids are strongly attracted by the external magnetic field. If we keep a piece of iron metal in a magnet, it is immediately attracted. Yes, it is strongly attracted, no doubt in that. And what are the examples? Iron, cobalt, nickel, gadolinium, and chromium dioxide. These are all very good examples for ferromagnetic materials, right? And here the atoms, suppose you take iron metal, okay, a piece of iron solid. In iron metal we have lot of iron atoms. These atoms contain more than one unpaired electron. Ferromagnetic material usually contain more than one unpaired electron. Okay, then next important one is, if we keep the ferromagnetic material in a magnetic field, it is strongly attracted. Then after some time, if you remove it, if you remove from the external magnetic field, the magnetic character remains for some time. This is one important property of ferromagnetic solids. Okay, why it is strongly attracted, why the magnetic character remains for some time? This you can explain based on what is called domain theory. Okay, in solid we have domains. Okay, domains means regions, different regions where the individual magnetic moments orienting in different directions, like this. Before keeping the solid in a magnetic field, okay, in all the domains, the orientations are completely random. The magnetic moments are completely random. There is no proper orientation. But if we keep the solid in a magnetic field, right, these magnetic moments starts to orient, okay, in the same direction of the external magnetic field. The orientations of the magnetic moments are same as the direction of the external magnetic field. Therefore, your material get magnetized. It is strongly attracted. I have told you, whenever the direction of the magnetic moment is same as the direction of the external magnetic field, then there will be attraction. So the solid get attracted. Okay, since all the domains are orienting in the same direction, it is strongly attracted. Then if you remove this solid from the magnetic field, this orientation of the magnetic moments will remain for some time. Okay, during that period, this solid will behave like a magnet. If you bring any iron needle near to this, that iron needle get attracted. But what happens after some time? As the time progress, okay, thermal agitation will occur, thermal agitation, slow. So this oriented magnetic moments starts to become random. Once it becomes completely random, the material will lose the magnetic character. This is the important information on on ferromagnetic solids. Okay, students, any doubt in this? Any doubt? Is this clear?
No, sir.
Okay, right, good. Now let me start the next one, that is anti-ferro. Anti-ferromagnetic solid, or you can also call it as anti-ferromagnetism. Okay, so this is fourth one, anti-ferromagnetic solid. Anti-ferromagnetic solid, what is meant by that? Here also, listen, this is very important. In anti-ferromagnetic solids, if we keep anti-ferromagnetic solids in the magnetic field, okay, they are repelled by the magnet. Anti-ferromagnetic substance, okay, they are not attracted, they are repelled. Okay, they are not attracted. Let me use the word like this: they are not not attracted. Not attracted means repelling. Not attracted by the magnetic field. Okay, it is not attracted by the magnetic field. Why? Is there any unpaired electron present or not? Yes, the atoms of this material, atoms or species, contains one or more, not one or more than one, contains more than one unpaired electron. No doubt in that. They have unpaired electrons. Students, keep this in mind. Whenever unpaired electron is present, usually material will show, or materials will be attracted by the magnet. Students, I repeat, whenever material contain unpaired electron, okay, the material get attracted by the magnet in general. But anti-ferromagnetic solids are some special solids. They contain unpaired electron, but they are not attracted by the magnet. Students, are you listening? Any doubt in this? Yeah, turn on your camera, everyone. Yes.
No, sir.
Yeah, turn on your camera. Yeah. See, it contains more than one unpaired electron. Okay. Whenever we generally say that when unpaired electron is present, the materials will be attracted by the magnet. In general, we say like this. But anti-ferromagnetic solids are special solids where the atoms contain unpaired electrons. Okay, more than one unpaired electron are present usually, but they are not attracted by the magnetic field. Why? What's the reason? Before that, I'll give you some examples. Examples for anti-ferromagnetic substance. A lot of examples are there. MnO, MnO2, okay, MnO2, etc. Many examples are there. I'm just showing you only few. MnO, MnO2. Listen, in MnO solid, let me take MnO. Here oxide charge is -2, manganese charge is +2. Okay, so manganese in +2 configuration, or manganese in +2 oxidation state. Students, listen carefully. Manganese in +2 oxidation state, the outer electronic configuration is 3d5. Manganese in +2 oxidation state, the outer electronic configuration is 3d5. That means it contains 5 unpaired electrons. So the d subshell 1, 2, 3, 4, 5. D subshell contains 5 unpaired electrons. So each manganese ion, Mn2 plus ion, they have 5 unpaired electrons. So this material is supposed to be strongly attracted by the magnet because they contain more unpaired electrons. But if we keep the material in a magnetic field, they are not attracted. Why? What's the reason? The reason is that we can explain this based on domain theory. Let me explain this with the domain approach. Students, observe this carefully. If we keep the material in a magnetic field, okay, so this is the direction of the external, the magnetic lines of force, and the materials have many domains. I'm just showing you only 4. What will happen before keeping the material in a magnetic field? The magnetic moments, because each manganese atom, see, each manganese ion has 5 unpaired electrons. So these 5 unpaired electrons will give a net magnetic moment. So each manganese ion has a net magnetic moment, and you know very well magnetic moment is a vector. Therefore, I am going to show these manganese ions, the net magnetic moment, as a vector. Before keeping in the magnetic field, the magnetic moments are random. Students, observe carefully. Before keeping in a magnetic field, the magnetic moments are random in all the domains. When you keep them in a magnetic field, if you keep it in a magnetic field, what will happen? See, the magnetic moment starts to align. Okay, here the magnetic moment starts to align in this direction. The magnetic moments in the other domain will align exactly in the opposite direction. Okay, here see I have shown 7 magnetic moments here, and here also I'm showing you 7. So when 7 magnetic moments, okay, are orienting in this direction, exactly same number of magnetic moment in the other domain will oppose this. Similarly here, okay, 1 2 3, suppose I'll show just 5. In this domain I have 5 magnetic moments which are orienting in this direction. In the other domain, right, exactly 5 magnetic moments will orient in the opposite direction. Therefore, what is the net magnetic moment, students? Net magnetic moment. They oppose each other. So, yeah,
0.
very good.
0.
It gets cancelled. Yes, it gets cancelled. So your material is not get magnetized. Okay, your material not get magnetized. That's the reason why anti-ferromagnetic substances, they contain many unpaired electron. Even then, okay, they are not attracted by the magnet. If you keep them in the magnetic field, they are not attracted. Why? Because the magnetic moments present in one domain and the magnetic moments present in other domain will oppose each other exactly in same number. They oppose with exactly same number. Therefore, the net magnetic moment becomes 0. The net magnetic moment. Now here, net magnetic moment, what I'm saying is the total, right? Net magnetic moment becomes 0. So the material is not attracted in the magnet or by the magnet. Is this clear, student? Is this clear? Okay. Yeah, this is very, very important. Why? Because the magnetic moments present in one domain and the magnetic moments present in the other domain, they oppose each other with the same number. Therefore, they cancel. Okay. Yeah, this is the property of what is called anti-ferromagnetic substances. Now, the last one called the ferromagnetic material. What is ferromagnetic material or ferromagnetic solid? The fifth type, ferromagnetic solid. Okay, what is meant by ferromagnetic solid? Is this solid is attracted by the magnet or not? Yes, this solid is attracted by the magnet. It is attracted. This solid, ferromagnetic solids, are attracted by the external magnetic field. By the external magnetic field, it is attracted. Is this attracted strongly or weakly? Okay, compared to paramagnetic, it is somewhat high, but compared to ferromagnetic, the attraction is somewhat less. Ferromagnetic materials are strongly attracted, but the attraction is somewhat in between paramagnetic and ferromagnetic. Here, are the species contain unpaired electron? Yes, species contain more than one unpaired electrons. The species contain more than one unpaired electrons. Unpaired electrons are there. When the species contain more than one unpaired electron, we normally expect that the solid should be strongly attracted because it contains more unpaired electron. But what I said is it is somewhat weakly attracted. Compared to ferromagnetic solid, it is weakly attracted. Why? What is the reason? Before going to see that, let me give the examples. What are the examples for ferromagnetic solids? Okay, Fe3O4. Right, this material it is called magnetite. Fe3O4. Right, in Fe3O4 is actually a mixture. You know very well, Fe3O4 is actually a mixture consists of FeO, ferrous oxide, and Fe2O3, ferric oxide. If you combine, you will get Fe3O4. So this oxide, Fe3O4, is sometimes called as ferroso-ferric oxide because it contains ferrous oxide. Here iron is +2 and ferric oxide iron is +3. So this material is called ferroso-ferric oxide. Okay. Now this is like this. We have many examples actually. We have Zn, Fe2O4. Many examples are there. Right? Now, why this material, though it contains many unpaired electrons, more than one unpaired electrons are there, but even then they are weakly attracted by the magnet. What's the reason? The reason is that suppose if we keep the material in a magnetic field, right? If we keep the material in a magnetic field, yeah, we have domains. We have domains in the solid. Right? Now what will happen? In one domain, the magnetic moments align in a particular direction. See here, I have taken 6 magnetic moments which are aligning in this direction. In the other domain, okay, the magnetic moment will oppose, but in unequal number. Here we have 6, but here I have shown only 4. Okay, so if you keep the material in a magnetic field, ferromagnetic material, if you keep the ferromagnetic material in a magnetic field, what will happen? The magnetic moments of one domain will oppose the magnetic moment of other domain. They are opposing, but not in equal number. Unequal number. Okay, that means you will get some magnetic character, correct? If they oppose in equal number, they cancel. Okay, what I am trying to say here is the magnetic moments of one domain will be is opposing the magnetic moments of the other domains in unequal number. Therefore, this solid has some less magnetic moment. Some less magnetic moment will come. Therefore, it is weakly attracted by the magnet. Is this clear, student? If all the magnetic moment orient in same direction, what will happen? Suppose if all magnetic moment orient in same direction in all the domains,
They're attracted.
they are strongly attracted. It behaves like ferromagnetic material. Am I right? But
Yes.
ferromagnetic material in which the magnetic moments of one domain and magnetic moments of other domain, they oppose, but they oppose in unequal number. Suppose here, see, I have six magnetic moments. Here I have only 4 magnetic moments. So if they oppose, 4 cancel. Remaining 2 will exist in the same direction of the magnetic field, external magnetic field. Therefore, they are weakly attracted by the magnet. Okay, is this clear, student? Any doubt? Okay, yeah. So this is what is called the ferromagnetic solid. So based on how different materials respond in the external magnetic field, we classified the material into 5 types: paramagnetic, diamagnetic, ferromagnetic, anti-ferromagnetic, and ferromagnetic solids. Okay, there are many examples are available. Here I have shown only a few. Okay, yeah, right. Any doubt, students? Any doubt? Any doubt in this?
No, sir.
Okay, so with this we have completed the solid state chapter. We will start the next chapter called